to you for the announcement. Hey everyone, hope you're doing well. I hope you had a nice Thanksgiving. It's hard to believe we only have 4 or 5 lectures left. I'm not sure if the semester has felt long to you or short to you. I think this year has been kind of a combination of both for me. Feels like forever and like it's flying by. So I'm not sure what to make of that. Okay, great. So I'm going to go ahead and over to Rohan real quick. He's got a quick announcement, and then we'll hop into today's lecture.
So last week, Arvind has posted one announcement and an assignment regarding extra credit assignment. So you guys can check it in modules. There's one extra credit assignment where you have to submit a video, a link of YouTube video which you will be making. You guys can find. So, Professor, can I share my screen?
Of course. Yep. Do you have permissions right now?
Yes.
Okay, great. Yeah, please go ahead.
So you guys can find the extra credit assignment over here in Intro to Computer Vision, and these are the topics where which you can select and do an extra credit assignment on. You have to make a video, upload it on YouTube, and give us the link to your YouTube video, and we can grade from there.
Great, thank you, Rohan. And just a little bit of context, the idea here is, for some folks who maybe had a bad quiz or had a bad programming challenge, we do drop the lowest. And I think we dropped the lowest programming challenge and quiz. Is that right, Rohan?
Yes, Professor.
Okay, great. So we do that. We have that in place. But also, if you still are concerned about your grade, then the extra credit assignment is just a way to boost your grade. So that's additional credit that'll help improve your score. So, and it's not too difficult. It's kind of called the state of the art on your own data set. It was part of the course last year, but we cut it because we didn't have enough time. But really, it's taking a paper and implementing it on your own data. So as far as the due date, I think we decided to make it due pretty late. Have we I don't think we've nailed down the final date though, right? Is that right, Rohan? I don't think we've finalized
Yes, we were
the date.
discussing it about 21st.
Okay, never mind. Sorry, we have. Okay, is that in the announcement, Rohan?
Not yet.
Okay, no problem. Okay, yeah. So we're discussing the 21st, Hernan. So that gives you about 3 weeks. Well, thank you, Rohan. Anything else before I hop in?
No, Professor.
Great. All right. Cool. Okay, well, real quick, just as we're kind of getting started here, what did you guys think of the guest lecture last time? Any comments, thoughts, things you liked, things that were confusing, things that were interesting? What did you guys think of Andrew Edelman's guest lecture? And we'll get it posted this week, just in case you missed it. Yeah, any thoughts? Any thoughts from the guest lecture? We have one more to go. Our last guest lecture will be, I'll go ahead and share my screen here. Actually, I'll share it in a second, but our last guest lecture will be someone I've never met before, actually, this guy named Thomas from Instagram. That should be really interesting. Instagram has gigantic computer vision data sets, right? Instagram and Pinterest always impress me with their computer vision, so I'm really excited to hear from Thomas. Any thoughts, though? Any thoughts on the last guest lecture? I thought it was fascinating, but I'm not the typical student, I guess. For me, as someone who's entrenched in an industry, I think if I think about my career, I usually work at companies that are small, that are trying to kind of innovate in a field. And currently I'm working for a company called Mariner. Yeah, so DevOps, Abhijit, yeah, totally. So Andrew Edelman, right, is a practitioner of kind of deploying these stuffs into manufacturing, and manufacturing is not quite mature enough to have like a full DevOps kind of stack. I think that Thomas B may have some interesting things to say about DevOps. That'll be interesting, Abhijit, yeah, because we haven't really, none of our guest lecturers this year have really done like computer vision for kind of like, I would say like, web companies, right? Like, so Instagram will be a different animal. They're at scale, they're a big web company. Yeah, so Monica, expecting more CI/CD, totally, yep. Yeah, he only could cover part of his stuff, basically. It's really interesting, yeah. Yeah, so Hernan and I also like that he showed all the bad stuff that engineers have to deal with. So it's super interesting. There's a bunch of different industries out there, and some are more advanced with their technology than others. And in some ways, manufacturing is behind. But it's interesting as you think about your career and what you want to do. It may not be at face value. You might say, hey, I want to go work for the most innovative company that's doing the coolest, newest stuff, right? Maybe that's exciting to you, for example. And maybe you want to work in the most advanced field, right? I will say though that if you look at some of the fields that are a little bit more behind, and I would say manufacturing is a little bit more behind than, let's say, autonomous driving. What it means though is there's huge room for improvement, so you can make a bigger impact. So at my last job in autonomous driving, you know, I spent a lot of my time trying to get our models to go from like 98% recall to like 99% recall, right? So like getting that last little percent of performance, and even beyond that, like 99.99, you know, like that last little smidge of performance. And that's cool, and there's a whole set of challenges that go with that. But you really have to be kind of fine tuning and in the long tail, like you're really making things perfect, right? Whereas in manufacturing, we'll go into projects where the existing systems may have an accuracy of 60%, which I know sounds crazy, but bringing in deep learning, we can go to 90%, for example, and make a huge impact. So I would say, as you're looking at what you want to do, if you do want to go into industry, then don't be afraid of some of the older industries. There's still a lot of cool opportunities, you know, things like manufacturing, finance, insurance, you know, things like that that you may not think are super innovative. There can be really cool stuff happening. And a lot of those older industries like manufacturing, what they do have is scale. So they do stuff at a really big scale, which is exciting. So if you deploy a new computer vision model that helps find defects in a product or something, and you're 10% better than the previous solution, if that manufacturer makes 10 million parts a year, right? All of a sudden, by changing performance by 10%, that's a million parts, right? You could have eliminated 10% of their waste or something, right? There's a huge impact you could have. So I would say, you know, keep that in mind. And then, yeah, I agree, Abhijit and Monica. I think that I'm very interested to hear Thomas next time, our last guest lecture, because he's at Instagram. I'm not sure if he's really on the DevOps side, but that area is super important. I could do a whole class on that, on deployment, right? It'd be pretty interesting. I would learn something by teaching that class. Okay, cool. Yeah, so Monica raises a great point. Sometimes these old industries won't hire a computer vision engineer. Yeah, it's super true. So a lot of the times, if you want to work in an industry like that, your best bet is often working for a smaller company that's trying to break into the industry. So like some of these big manufacturers may not hire you, right? Because you're kind of like too big of a jump or too big of a risk for them. So a lot of people, what they'll do is they'll work for a startup that's trying to get into the industry, or they will start their own company, right? But yeah, you're right. A lot of these old companies are not going to be, although you're seeing that change some, but it's true. Some of the more conservative companies are not going to be hiring deep learning engineers. But deep learning will hit them. It's just a matter of time. And it might not be through direct hiring, though. It might be through a company that they hire. Does that make sense? So, you know, Ford might not hire a bunch of computer vision engineers. They actually have, but a big company like GM or something, they may hire some tiny little startup with 5 people to do some of their computer vision work. So there's other ways in, I guess. Oh, right. Cool. Right. Okay, so let's hop into today's lecture. Let me go and get my screen share going. If I lose audio quality, please let me know and I will turn off my video. Okay. All right, cool. So here's our schedule. I hope you all had a really nice break, and then you had 2 things due yesterday. I hope those things went well. There's a few kind of open issues around the programming challenge. Rohan, I'll catch up on that with you later today or tomorrow. But I hope the last programming challenge went well. You have 1 more left. And I'm going to introduce the last programming challenge just in a minute. But you have 1 module left. So you've been through deep learning. We didn't have a chance to cover GANs as much as I wanted to. We'll see if we can squeeze in a little more material about GANs, but you do have some reading you can do. So we covered deep learning. I hope it was interesting. I think deep learning is fascinating. Now that we've finished the deep learning module, any comments, any thoughts on deep learning, right? So you've kind of been through it. You've seen how they work. You've trained a model. If you finished the programming challenge, you've submitted a model. How did deep learning compare to what you thought, right? Any comments or thoughts about deep learning? Black boxes, sure, yep. So it is kind of a black box. And yeah, Ashish, I agree. It is harder than it looks, right? So people, you kind of go, you read the news, the articles and stuff, and it looks like training a neural network is like really easy. But a lot can go wrong, even with a library like FastAI or PyTorch, right? There's still a lot to do. Yeah, absolutely. Did you guys let me ask you one more question. I always debate this. So Ravina also agrees it's harder than it looks. Yeah, I agree. So I always debate if we should actually start the class with deep learning. Did you guys like learning about neural networks, like learning machine learning then neural networks, then deep learning, kind of like ramping up progressively? Or do you think it'd be better to start with deep learning with like the, production grade stuff and then kind of take it apart slowly and go like deeper into it from there? Throw it in the comment. What do you think? Do you like doing it in that order? Or do you think it'd be better if we actually had started the course with deep learning? Who is... I don't quite follow your answer, Sai. Okay, Jagadish likes the current. If you have any thoughts on this, let us know. Start with chaos. So Sai wants to start with chaos. Okay, yeah. I think it depends on how you what your learning style is. Some people like to kind of build things one step at a time. So Manessa says start with deep learning. We could consider it. It's definitely an option. That way you kind of have the cutting edge stuff at the beginning, and then we slowly take it back apart. So Ravina likes the approach we took. Sean wishes there was more fundamentals. Yeah, that'd be nice, Sean. I wish I had time, right? I got to get you guys to deep learning because it's so important. But yeah, I would like to spend more time on fundamentals. Yeah, so Abhijit says the bottom up helps appreciate what the libraries are doing. Yeah, totally. Yeah, I've thought about this a lot, and I think I'm about 65% in favor of the way we do it today. But there's arguments to be made for doing it the other way. My learning style is more synthesized, start with small and then build up, basically. Yeah, it would be nice to have more time on deep learning. I agree, absolutely. Yeah, and deep learning first could be overwhelming because you got to remember that a decent chunk of our class has never done Python before, right? So that's a big learning curve. More deep learning, sure, yeah. Whoa, so Sai says 80% of the class doing deep learning. That'd be pretty cool. That would be, the name of the class would be Deep Learning for Computer Vision, right? Which maybe UNCC should offer that. That'd be cool. All right, cool. We could talk to Dr. Shin. He maybe UNCC could add that as a course. All right, cool. So let me go ahead and introduce the last module. I appreciate your feedback. Thanks for chatting with me about that. So yeah, this is the last module. So here's the GitHub page for it. The last module is called the 3D world. And yeah, we could easily spend 2 more weeks on deep learning, right? There's way more to say. But if I taught you computer vision and I didn't include anything about the 3D world, I think I would be doing you a disservice because this is a huge part of computer vision. Deep learning hasn't fully infiltrated it yet, but it's starting to. But a bunch of computer vision, especially historically, a huge body of literature in computer vision is on the 3D world. It's about cameras and calibration and point clouds and stuff like this. So if I didn't cover this, I think I would be doing you a disservice. So we need to spend some time on it, and it's a really cool area. And there are advances. It's not quite as cutting edge as deep learning. There's not as much happening, but there is still some really cool stuff happening. This map is from a company called Mapillary. And this is really cool. Let me just talk you through it for a second. So what this company has done, so they provide maps for things like autonomous driving. And actually, let me ask the class. So let's say that you joined a new company. Let's say you were hired as CTO. So the company hired you and said, hey, you are the chief technical officer of XYZ mapping company. We need to go make a bunch of maps, right? And I want them to be 3D. I want 3D maps that we can sell to. There's a bunch of use cases for maps. Google Maps can help you get around a city. Autonomous driving maps can help autonomous cars navigate very tricky, narrow situations. There's a bunch of other applications for maps. But let's say you worked at a mapping company. And mapping companies can be worth a lot of money too. I think Nokia bought a mapping company called Here for like $3 billion a few years ago, something like that. So anyway, it's a good business model. Now let's say that you were hired as a CTO of a mapping company, and the company had no technology yet, nothing, right? What would you tell your CEO to do, right? How would you start making maps? What would you do on day one? What do you think? Throw it in the chat window. How would you make a map? Oh, that's pretty cool. So Sai mentions this is the AR maps uses. Yeah, sure, definitely. Yeah. So what do you guys think? How would you go make a map, a 3D map? Hire people who already know how to make maps. That's a good answer, Abhijit. Let's pretend that's a good answer. But what would you do, right? If let's say you had $100,000, a very low budget or something. Let's say you have to make a map from scratch. So Austin says gather data, which I like. How would you gather that data? So Adam says hire new geography grads to drive new beetles around the country with LiDAR on the roof. Yeah, Totally, totally. Cool. Let's expand on Adam's answer a little bit. So Adam mentions a technology called LiDAR. What is LiDAR? Does LiDAR fit in computer vision? What is LiDAR? If you know what LiDAR is, throw an answer in the chat window. Yeah, so LiDAR uses laser. It uses laser. So it's an active sensor. It's similar to cameras in some way, and the new iPhone does have a LiDAR, which is pretty freaking cool. But what do I mean when I say it's active? So some people will call cameras, they call them passive optical sensors, passive optical. LiDAR is not passive optical, it's active optical. Why is LiDAR active? Well, yeah. Well, what does it do, right? So, yeah, it shoots out a laser. Really, it's not. It's actually not a laser. It's a. Sorry, I shouldn't have said laser. It's a. Well, is it actually? I need to check. I'm not sure. It sends out electromagnetic pulse, and it times how. It's a time of flight sensor, so it sends out a pulse of. I can't remember if it's supersonic or infrasonic, but no, sorry, not infrasonic. I can't remember the frequencies. It's not optical. You can't see them. I think they're maybe a little bit above the visible spectrum, but it shoots out. I think it is lasers. Anyway, shoots them out, bounces them off things, and then based on how long it takes the light to come back, it can estimate how far away things are. So you can do that, right? That's certainly a cool way to collect data for mapping by using a LiDAR. But here's my question to you. Are there any reasons you would not want to use a LiDAR, right? So LiDAR is a great sensor. It gets really high quality data. Yeah, so as she says cost, it's expensive. Yeah, they're expensive and they're also very finicky. So if you didn't want to use a LiDAR, you could use, well, let me ask you this. What else could you use? Let me back up a little bit, right? So yeah, Hernan says stereo camera. So stereo is interesting. Stereo was really popular in the 2000s. It's really fallen out of favor. You can do some really cool stuff with it, but you don't have to actually have stereo to do 3D, which maybe sounds a little confusing, but we'll talk about why soon. So stereo is a good idea, but you don't even actually have to have that. Really, and what I want to kind of get to is this map I'm showing you. So this 3D map that we're navigating through of Amsterdam, this was made only with single images from phones. So that was it, and different phones at that. So what we're going to talk about in this module a little bit, among other things, is how you can make a 3D model of something using only 2D images. It's really, really, really cool. The math is awesome. That's what we're going to be talking about. And in your programming challenge for this module, this is kind of an open-ended challenge. It's pretty fun, I think. Your job is actually to make a 3D reconstruction of something. So here's my 3D reconstruction that I made of a brick ball in a cylinder. And what's I think a little different about this challenge is you're not going to be writing any source code. So you're going to be using a library called OpenSFM. So SFM stands for Structure from Motion. You will be using this library on your own data to make a 3D model. So that will be the challenge for this programming, this module. And we've seen some really cool submissions so far. So last year we had some really cool ones. Actually, no, we didn't do this last year. Sorry, the first year we had some really cool submissions. So that's going to be your challenge, is taking a bunch of images of something and making a 3D model. You could do like your house, you could do your apartment, you could do something small, you could do something big, but that's going to be what you're doing. And yeah, so as far as the groups, yeah, so we do this in groups because it takes a little bit of work to take all these images. So Rohan, let's make sure we discuss this. Will you make a reminder, Rohan, that we need to discuss how we will pick the groups, because this is a group project. We may do the same groups as the course project. It's a good idea. I think we did that before. So Rohan, if you could just make a reminder to discuss how we'll assign groups for this this challenge.
Yes, Professor.
Thank you, Rohan. Awesome. Great. So yeah, so Hernan's asking if we can make a 3D map or an object like this. So really, structure from motion can do both, and we'll get into that in a lot of detail. It's a really good question. So that's your challenge, and here's the instructions. So I'll leave that alone for now. I want to get into the meat of today's lecture. So let's dive into it, right? Let's get into how do we really make 3D computer vision happen, right? How does this work? So here's our lecture for today. And the name of this lecture is the Pinhole camera. And we're going to talk about this model of a camera. So it turns out to do anything in 3D space, you really have to start with a model of the camera. So that's what we're going to start. And you could say the class is a little bit backwards, because shouldn't we start a computer vision class with discussing cameras, right? But we're waiting till the very end. But here we are. So today we're going to learn how a camera works. So what I want to do to motivate this lecture is I want to show you what you can do with the math that we're about to learn. So this was an animation that I made at my last job. We used to use this in some of our demonstrations. Yeah, so Sai is asking, is that the real shape of the track? Yeah, so let me just kind of talk through it here. So this is, great question, Sai. So this is the same data set you've seen before, or a similar data set at least. So you might recognize this from the Autonomous Driving Challenge. This is the test track at the company I used to work at. And what I'm doing here is you can see, like, look, I've taken all these images. It's the same data you see in these images. And I've actually stitched them together into like an overhead view to make a map. Inside, this is the real shape of the track. And in this lecture, we're going to discuss most of how you do this. I am going to leave one thing out, which is how do I know where the car is? To figure out where the car is, I'm using, on this car, we have a very expensive IMU. An IMU is an inertial measurement unit. That gives us very accurate location information for the car. So I'm using that, but you don't actually have to use that. You can actually just use images alone, but that's a little bit of a harder problem. So here I'm going to show you how to do most of this, except for the location information, basically. But what I've done here using the math we're about to cover is I've made a map of this track just using images plus location data. So let's get into how we actually make this happen. Okay. So it's math time. There is a great book on this. So whenever anyone asks me about this or asks questions, I always refer them to Print's Computer Vision. It's available online. You can buy it on Amazon for $70 if you want a hard copy. But chapter 14 of Print's Computer Vision, where is you'll find a link on this page, but I'm going to borrow some figures from him, and the presentation is just really, really clear. I've read all the books on this, at least most of the books. This one is the best in my opinion. Okay, so we're going to start with a model of the camera. So this is a model of a camera, and we've waited till the very end of class to discuss it, but I think that's fine. So you have some object in the world. Here it's like a star or something. A camera really consists of there's two important things. So in the pinhole model of the camera, we have a tiny point. In this model, it's actually infinitesimally small. We have a point where all of the rays of light come through, and then those are projected onto the back of the camera where you have your image sensor. So this is reasonably close to how real cameras work. There's other things that actually happen in real life, but this is really a pretty good model of how a camera works. You have rays of light come in, they go through a tiny little hole, and they get projected onto the back of the camera where you have your image sensor. It turns out mathematically, it's easier to pretend that your sensor is actually in front of the pinhole. So this is called a round. And let's pretend, to make our math easier, let's pretend that our virtual image on our image sensor inside the camera, let's pretend it's actually on this side. So we're going to treat our math this way. So I hope that makes sense, and we'll get into this in more detail. But that is the simple model of the camera that we're going to be using. So here it is broken out with some variables on it. So here's our star again in world coordinates. Here is the optical center of the camera. So that's that pinhole that we were talking about. The other name for it is optical center. In our image plane, again, I'm showing the image plane in front of the optical center. In reality, this image plane is behind the optical center and the image is flipped. But here we're going to flip it around, pretend it's in the front, and all the math will come out the same. We just don't have to worry about minus signs for flipping things over. So here's our camera model, and I want to talk you through the variables. So notice that I've put the origin of, and this whole lecture is about 3D computer vision. So we're going to have three coordinate axes. So here we've defined the origin of our coordinate system here. Conveniently, we've put our origin at the optical center of the camera. And we have three axes. We have the U-axis, the V-axis, and the W-axis. The W-axis goes directly down the focal length of the camera, so right down the lens of the camera. The U-axis is left to right, kind of the X direction on the image, and the V-axis is up and down. So this is the coordinate system we'll be using. And for any point in the world, right, so if you think about, if I go back up to my kind of track animation here, right, if I think about some point in the world, right, so imagine some place, you know, on the track in front of the camera, right, that's some point in the world. That point, we can describe its location using world coordinates. We need three of them because it's in 3D space. And what we're showing here really is that this W value, this point on the star, That's a location in world space, and we've parameterized it using our 3 variables. So we're in 3-dimensional space. We have a u, a v, and a w axis. And that's how we're choosing to describe the location of objects in the world. So that's our world coordinate system. Now, we also have an image coordinate system. I hope that makes sense. We've got the world coordinates. There's 3 dimensions. In our image space, we only have 2 dimensions because you have points in the real world that are projected, right, down into a 2-dimensional image plane. For that 2-dimensional image plane, we'll use the coordinates x and y, or the names x and y. And just like with our images, we'll put x and y in the upper left-hand corner. We're actually going to move them here temporarily. I'll get into that in 1 second. But this is the model. So this is the model that we'll use to map image to world and world to image. And let me just motivate that a little bit more. So what I'm trying to get you to do by talking you through this lecture is I want you to kind of play a role in figuring out, we'll talk through it together. I want us to figure out the math that lets us map world coordinates to image coordinates and image coordinates to world coordinates. Because if I want to make a map, right, if I want to solve a problem like this, right, notice that all these pixels, right, they start out in image coordinates, right? We have like, I know this pixel's at like, you know, image coordinate 800, 400 or something, right? And what I want to do is I want to put that point, I want to figure out where is that in 3D space? Where does this point exist in the world? So to do that, right, we need to solve these equations. Well, we need to first figure out what the equations are, excuse me, which is what we're about to do. I want to figure out the equations that let us go from x and y to u, v, and w, and from u, v, and w to x and y. I want to figure out that mapping. That mapping is really the key of the pinhole camera model, and it really is the center of a ton of math that we'll do in this model. Okay, so that's our job, is to find the mapping between image and world coordinates. And I would actually claim, I'm going to go ahead and make a claim, that you're going to be able to start writing down some math for that mapping without actually thinking too hard. So let me switch my screen share and go ahead and start thinking. Let me switch my screen share to something I can draw on. Cool. All right. So that's coming through. Great. All right, cool. So here's what I want to do. I want us to just get started. We're going to take it back to high school math for a minute, and we're going to discuss how we get started here. It's really not bad, I promise. So the first thing I'm going to do is so I told you the origin is up here, right? I'm going to actually move this down here temporarily to make life easier. So let's say that this is the origin for now. So we have y going down right here, y, and I have x going to the right like this. So that's y and that's x. So I'm going to move this origin. Now I really want to challenge you for a second. Let me change colors. Okay. All right. So now, let me move this just a little bit so you can see nicely. Okay, cool. A little bit smaller. There we go. Okay, cool. All right. So we have u, v, and w, our world coordinate points, right? And we have x and y, our image points. And let's just take one dimension for a second, right? Let's just think about the vertical dimension for a second, right? And I'm going to draw kind of a cross section of this. I'm going to draw kind of the vertical cross section. So I have my w axis going this way. And I think I might, to make life easier, yeah, I'm going to draw the same kind of dotted line, but I'm going to do it here. Okay, there we go. So what I want, so this is my optical center, and I'm just kind of drawing it from the side view, right? And here, let's say my image plane is here, right? Okay, here's the center of my image plane. So this point here corresponds to this point here, and I'm just kind of drawing a simplified version of this. Now I want to fill in some numbers, right? Let's say that our world coordinate point is like right here, for example. What I want to start thinking about, and again, we're just trying to find the mapping between our world coordinates and our image coordinates. So given the coordinate system we're in, let me go ahead and ask you this. What is this distance? What is this distance here? This is in world coordinates, right? So this is the world, and this is the image plane on the camera. What variable represents this distance here? What do you think? Yeah, it's v. Yep, perfect. So it's the same as this dimension, and I could put a minus sign here because we're going down from the axis, but I'm going to keep things simple for now. I'm just going to call this v. So this is v, right? This distance is v. Perfect. And then what about here? What is the distance from the optical center to the point in world space? What is this distance here? W, yep, thank you, Ashish. Awesome, cool, so this is W. Okay, cool. What is, let me change colors again real quick to pink, okay. What is this distance? So from here to here, from the optical center to the focal plane, or to the image plane. What is this distance here? What have we called that? Focal length, yep. And we haven't talked about focal length too much. Focal length is just the distance between the optical center of the camera and the image plane. So if you look at like really big zoom lenses, right, on big cameras, those have very long focal lengths, and really wide angle cameras have very short focal lengths. Okay, so that's F. And then finally, the last thing we're missing is this variable right here. What name did we give this distance right here? What name do we give this? Yeah, it's Y, right? Cool. Okay. So let's take it back to 10th grade or 11th grade or 9th grade or whatever, and let's use some similar triangles. So someone please tell me an equation. What over what is equal to what over what in terms of F, Y, W, and V? Please give me an equation that uses all four variables, that uses similar triangles. Because once we have this equation, we're going to be like halfway there. So Abhijit says, let's write down what Abhijit says. Abhijit says V over W is equal to Y over F. Let's see if I agree with Abhijit. I think I do. Let me look. Let's see here. Okay. So V over W, so this is like the short side over it's the two legs of the triangle, really, short over long. Yeah, so Abhijit's saying that this to this is equal to this to this. I totally agree. So Pooja has given a different answer. She says Y over F is equal to V over W. Yep, actually that's the same answer, just flipped, yep. And there's another way we can write it too, but yeah, absolutely. So I hope this makes sense. You know, using similar triangles, we've started to find a relationship between world coordinates and image coordinates just by using similar triangles. Like that's it. We could rearrange this, and we're going to do that in a minute. I think what we're actually probably going to do, yeah. So we're going to focus on going from world to image coordinates in a second. So I'm going to flip back to the lecture notes, but I think what we're going to do is we're going to say Y is equal to V times F divided by W. So I've just moved the F over. And what this is saying is that if you have some point out in the world, right, that is at location V comma W, right, and the focal length of your camera is F, then it will land at point Y on your image sensor. So that's the idea, right? So just using similar triangles, we've already developed one equation that maps from world space to image space. Okay, so let me shift back here to my lecture notes, and we'll keep moving. I hope that makes sense. Really, the math here is not too crazy. It shouldn't feel too crazy so far. It'll get a little more complicated, but it's really not too bad. So let's see. So yeah, here we go. So I think this is the same equation, Y over F. Yep, this is the same equation we just talked about. So this is the kind of the view from the side to get this equation. If you take the view from overhead, you'll get this equation. So this is the same deal, but it's in the X direction. So you get those two equations. Okay, so we're getting started here. So now we're going to rearrange these two equations like I just mentioned. And I'm already making that pretty big. Can I make it a little bigger? Let's see. Yeah, it's a little bigger. So I'm rearranging these. So this is image space, and this is world space. So we're mapping from world space to image space. And now we need to go back and fix a few assumptions. The first thing I want to fix is our units. Let's talk about units. We haven't mentioned this at all. Let's go back to units for a second. So let's assume for a minute that our units in the world space, let's assume that these are millimeters, which is a pretty common unit to use. Let's say that U, V, and W are in millimeters. If U, V, and W are in millimeters, and we just talked through how our equation worked, you just saw our equation, right? Then if we solved our equation, what units would X and Y be in, right? So if you plugged in U, F, and W, and these are in millimeters, millimeters, and millimeters, right? What units would X be in naturally? What units would it turn out to be in? Yeah, it's millimeters. So it's because we have millimeters times millimeters divided by millimeters. So you have 2 up here, 1 down here, so 1 cancels. So yeah, so X is in millimeters, right? Now remember that X is the position on the image, right? It's actually the location in image space. So I don't know what you've been doing in this class exactly, but I doubt that you've solved any problems using the location of a pixel in image space, or sorry, in millimeters. What units would you prefer X and Y to be in? What units would be nice and easy to work with? What would you like? Pixels, yes, thank you, Jagadish. So really X and Y should be in pixels, right? So let's handle that problem now. So here we are. So there's another variable we need to bring in. So to convert from millimeters to pixels, the answer to that question depends on which camera you're using. If you have a camera that has very small pixels, if it's a very high resolution camera, you're going to get a different answer than if you have a camera with very big pixels. So we can parameterize that by using, we're going to call it dx and dy. This is the photoreceptor spacing here in the x direction. So it's the number of pixels per millimeter that a sensor has. And here it is in the y direction. Generally, the photoreceptor spacing is the same in both directions. So usually we're going to just call it one number, but it could be different. You could have a camera that has a higher density of pixels this way and less of a density this way, but very rare, but it could happen. Okay, so all I have to do to convert x into pixels is just multiply by dx. So here's my old equation, and I'm just multiplying by pixels over millimeters to get pixels, excuse me. And I have to multiply y by dy. Now in practice, what usually happens is practitioners will multiply f, the focal length, by dx, and they will roll that together into one parameter called phi x. This is often called the focal length parameter, and it's the focal length times the photoreceptor spacing. There's a really nice interpretation for phi x and phi y. What it turns out to be is it's the length of the focal length measured in pixels. So if you could measure the focal length of your camera in pixels, that would be phi x and phi y. So that's generally how we parameterize this. And now all of a sudden we have two equations that not only map from world to image space, they map to image space in pixels, which is great, as long as you know phi x and phi y, right? You have to know those things. We'll get into how you figure them out soon. But if you know those things, you can do this math. Okay, I would like to now address one other issue. And that was the issue that I created. Remember what I did? I said, let's temporarily move this origin. Let's put it at the principal point to make life easy, right? But in reality, you know that when we process images, we almost always put the origin in the upper left-hand corner. And it's kind of inconvenient to have the origin at the center. So that's also actually very easy to adjust for. All we're going to do is we're going to add an offset to our equation. So here it is. Let me make these a little bigger if I can. I should really do this in the first place. Okay. So I'm going to add what's called delta x and delta y. And let me just ask the class. Hopefully this is kind of making some sense. I hope. This can be a lot of math, but I promise, like the underline, it's way simpler than neural networks, I think. So what are delta x, what are delta y, right? If you had to explain this to someone who didn't know a lot about cameras, what would you say? What do these parameters, delta x and delta y, what do they represent about your camera? Yeah, so it's the center of the image in the x direction, right? Let me push you a little bit further. So you're right, absolutely. Shift parameter, change in x and y, totally, right? Let me push you a little further. Assume with me for a moment that the principal point is at the center of your image, right? And that's generally that's close to true. It's not always exactly true, but it's close to true in practice for most cameras. Assume the principal point is right in the center of your image plane. Now, with that assumption, let me ask you one more question. What are the units of delta x? What do you think? What are the units of delta x? Pixels, right? Yep, it's pixels. Good, okay. So if I came to you and I said, hey, here's a camera and it has a delta x of, let's say, 640. So delta x is 640. And I said, okay, you're also allowed to assume that the principal point is right in the center of the image plane. What could you tell me right away? If I said delta x is 640 pixels, the principal point's in the center, what could you tell me right away about that camera? Yeah, you could tell me the horizontal resolution. What would the horizontal resolution be for that camera? It's 1280. Yeah, totally, right? It's just double, right? So this tells us in pixels where the center is, or the principal point is, excuse me. And if the principal point is in the center, which it usually is, then this is just going to be half your resolution. So this is half of your horizontal resolution. This is half of your vertical resolution. I hope that makes sense. So that's the idea there. Okay, let's keep moving. So in practice, we've talked about 4 parameters, delta x, delta y, phi x, and phi y, the focal length parameters and the offset parameters. In practice, we throw these all into a matrix. And we'll talk about why in a minute, right? Why would we do this? But typically we throw it into a matrix we call delta, or sorry, lambda. And my question actually, I don't have a question, do I? I'm just used to asking you guys questions. But your question to me might be, why put this in a matrix? And it'll become clear in a minute. But this intrinsic matrix, this is called the intrinsic matrix. And this matrix describes kind of how your camera works. So these variables really describe what your camera does with the pinhole model. And these parameters will be different for different cameras. And this is called the intrinsic matrix. Okay, so let's do my favorite thing. Let's ask you guys a question. Let's get you thinking a little bit. So here's the first question of the day, and it's not a poll question. It's going to be a free response kind of question. But I think I'll still pause and give you a minute to think about it, because I think it's worth thinking about on your own for a minute before I give you the answer. So you can tell I made this question a few years ago, back when iPhone 6s were cool. This is when I had an iPhone 6 back in 2016 or something, 2017, I guess. So what I had the class do is compute the intrinsic matrix for my iPhone 6. So I looked at the spec sheet. The focal length of my camera was 2.65 millimeters, very short. The field of view of my camera was 73 degrees. So that's the horizontal field of view. So if you kind of take the overhead view, this interior angle is 73 degrees. And the resolution is full HD, so 1920 by 1080. And I'm allowing you to assume that the sensor is perfectly centered along the optical axis and that you have the same photoreceptor spacing in the vertical and horizontal dimension. So based on this information alone, I would like you to estimate this matrix, right? So I'm gonna go ahead and go on mute for about a minute, maybe a minute and a half. I'm gonna work on my solution, and please work on your solutions. I hope this question makes sense. I would like you to estimate the intrinsic matrix for an iPhone 6. Here's the focal length, here's the horizontal field of view, here's the resolution, and you can assume that the horizontal and vertical spacing are the same, and that the optical center is at the principal point is right in the center. Okay, cool. So don't give me your answers yet. Just go think about it. So take 60 to 90 seconds, and then we'll pick up from there. Okay, everyone, so hopefully you've had a chance to think about it here. I didn't time it exactly, but it felt like a little bit of chance to think about it. So let me go ahead and talk you through my solution. If you have an answer, great. So let me kind of talk you through what I'm thinking, and we'll see how this matches what you've done. So let me share the screen that I can draw on. Okay, there it is. Cool. All right, so here's my thinking. Let me walk you through it. There's two parts to this question, and the first part's way easier. All right, so the first part is just delta x, delta y. So I think Hernan has already given us an answer, but anyone else, does anyone agree, disagree? What do you think? Let's start with delta x. What do you guys think delta x is for this problem? Yeah, 960. And how did you arrive at 960? Why do we think delta x is 960? 960. Yeah, it's half the horizontal resolution. Perfect. Okay, what about delta y? What is delta y? What do we think? 540. Excellent, cool. Okay, so those are pretty straightforward. The last one is a little bit harder, and I did this on purpose because I wanted you to kind of think about the camera model. This is very much a kind of question I'd ask you on a quiz. So there's a bunch of ways to figure these out, but I didn't give you, like, notice I didn't give you the pixel spacing, right? You couldn't just multiply two numbers together, for example. You have to think a little bit harder. So let me show you how I did this problem. And there's other ways to do it, but let me show you how I would think about it. So I have made an overhead drawing here. This is an overhead view. There's some point in world space here. I know that this is U, this distance here. This is W, this distance here. This is X, this distance from here to here. And then lastly, I did give you a little data about the angle, right? So if the horizontal field of view, if that's 73, right, then what would this angle be, right? What would this, it's gonna be useful in a second, right? That's not a very nice line. What would this angle be here? What do you think? Yeah, 73 over 2, which is like, what is that, 36 and a half, something like that. I think it's 36.5. Just chat me if I'm wrong. So I believe this to be 36.5 degrees. And a way to solve this problem that I like is to actually use a test point. So I've set up a test point in world coordinates here that's way at the edge. It's like at the very, very edge of the image sensor. Hopefully that makes sense. So it's way on the edge of our field of view. It's way at the right. Because if I pick a point there, I'm going to actually know what x is right away, and I can solve the equation. So I'm going to grab this equation here, and I'm going to solve it to figure out what we're missing, which is this. I'm going to solve it for this. Let's get into it. So what would x be if our point is way on the right side of our camera, right? If our point is way on the right side of our camera, what does x have to be? What do you think? Good guess. So Abhijit says 960. Close. 1919, sure. So yeah, if it's the very most right pixel, right? 1920, right? So 1920 is what I'm really looking for. If you were way on the left side of your camera, it would be 0, right? So yeah, 1920 it would be a point way on the right side. That'd be the x value for a point that's way on the right side of my camera, right? Okay, I hope that makes sense. Now we don't actually know u. I've just picked some world coordinate point, but we're gonna do something clever about that in a second. So we don't know u. We don't know w, right? I've just said, hey, there's some world coordinate point out there. And that's fine. And I'm going to go ahead and write, I'm kind of breaking this apart on purpose. So we have phi x, which we're trying to solve for, right? And what did we say? What did we say? I'm just taking this equation, right? What did we say delta x was again? $960, thank you very much. Cool. Okay, so here's our equation. So you might be saying to me, Stephen, you're dumb. This is not going to work because look, you have 3 variables, right? You still have 3 variables. What are you going to do? Any ideas? How could we, I'd like to only have one variable. I'd like to only have phi x be the one variable, right? What can I do? Any ideas? How can I eliminate 2 of these variables? Any ideas? What do we know about u over w? That's true, u over w is x over f. Sure. Let me give you a hint. I would like, what piece of information have we not used yet? So we haven't used f, I guess, right? But what else have we not used? What piece of data have we not used? Focal length and what else? We've also not used the field of view, right? We haven't used the field of view. So this takes a little bit of a creative jump, but it's not too crazy, I promise. So the field of view can actually uniquely determine u over w in this case. Let me show you what I mean. So we start to think about this for a second, right? So I'm interested in the ratio of u over w. if I think about this right triangle here, right, the short leg is U, the long leg is W, right? What trigonometric ratio connects the two legs of a triangle? What trigonometric ratio? What piece of trigonometry could help us with the opposite and the adjacent side of a triangle? Mm-hmm. Thank you. Yeah, so tangent. Yep, totally, right? So if I wrote something like, let me write it over here. So like if I wrote tangent of 36.5, right? 36.5, cool, equals, right? That would equal, it's the opposite over the adjacent, right? It equals u over w, right? Hopefully that makes sense. Tangent of 36.5 equals u over w, because we're right on the edge of our triangle here. Okay, and u over w, right? That's kind of a nice thing, right? Because it's the same exact thing we have here, right? So I've kind of done a little bit of sneakiness here, but it's not too crazy, I promise. We're actually not going to end up using the focal length here, which is interesting. But we can just solve this equation now, because tan 36.5, that's just a number, right? So I might, yeah, let's do it, right? So we don't have a ton of time left, but you know, I like walking through these things. So here's my trusty TI-84. So make sure I'm in degree mode. Let's see. I don't use this thing as much as I used to. Okay, tangent of 36.5. So I get wait, am I in degree? Oh yeah, that's right, cool, okay, great. So yeah, I get 0.739. I'm gonna say 0.74. So if you wanna check my math, please do. I get around 0.74 for this value, so I can just plug in 0.74 here, right? And I get a phi x here, and I get a plus 960, and I get a 1920 over here. Okay, Monica gets a different number. Can someone else check my math here? Tangent of 36.5 degrees. Siri told Monica. Okay. I don't think it should be negative, maybe. Can someone else check our math here? Tangent of 36.5. I'm going to question Siri on this one because I'm in degree mode. Yeah, I believe it's 0.74. Okay, yeah, 0.73, 0.74, great. All right, cool. So I'm gonna go ahead and solve this equation. So I know my screen's a little bit of a mess here, but we're gonna subtract 960 over to this side. So I'm gonna do 1920 minus 960, which is just gonna be 960, I think. And then I'm gonna divide, yeah, I think that's radians, Ravina, yeah, that's right, yep. And then I'm gonna divide by 0.74. Cool, all right, so I get 1297. I get 1297. So that would go right here. 1, 2, 9, 7. Cool. Okay, like 0.3 or something. Okay. Okay, cool. All right, so I hope that makes sense. I've solved this equation. I get 1297.3. And what about this value? What would go here? What do you guys think? What about this very last value? What about phi y? Any ideas? How can we find phi y? No ideas so far? We should make it, this should be a prize. Don't think too hard. Remember that we're assuming that we have the same vertical and horizontal spacing, right? If you have the same vertical and horizontal spacing, remember that this is just the focal length times the spacing. So these two are going to be equal. These actually are going to almost always be equal. So yeah, it's the same. So this is 1297.3. Okay, I hope that makes sense. So this is the intrinsic matrix for my iPhone 6 camera. All right, cool. So Ravina asked a quick question. She says, we use tan for the right angle triangle or any, oh yeah, so tangent, sine, and cosine. Good question, Ravina. Those only apply to right triangles. Great question. You have to have a right triangle. Here we do have a right triangle. You generally will with these kind of problems. So this is a right triangle. Good question. Cool. So Abhijit says that's what's confusing to me. Should it be the dotted pink? Yeah. Yeah. So really, I know my drawing's not great here. I encourage you to go back through this. This is the triangle I'm looking at here, right? This triangle and then this triangle, right? These are our two similar triangles in this case. And it always almost comes down to similar triangles. Okay. So again, this is exactly the kind of question I'd ask you on your quiz. Make sure you feel good about these. Feel free to ask the TAs or myself questions. This is kind of the bread and butter, simple techniques that that are important in this module. Okay, we have about 20 minutes. Let's keep cracking. So We found the intrinsic matrix for my iPhone 6. Pretty shocking. So let's keep moving here. But at the end of the day, just remember that using this math, you have to do all these steps. But when you do all this, you can make really cool stuff like this, right? So it's all little pieces that go together to make some really neat stuff happen. Okay, so that's my iPhone 6. And now I think I'm going to ask you some more questions. Yeah, I'm going to ask you some more questions. So let's get into it. So here's my next question for the class. So what I'm asking you to do, I've given you, here's the picture, here's this picture, here's the equations, here's the intrinsic matrix. So I'm giving you the intrinsic matrix, right? I'm giving it to you. I've kind of just made one up that's kind of similar to the one we just figured out. Notice this 960 would be half of the horizontal resolution. So this would be a 1920 by 1080 resolution camera. That's the intrinsic matrix. And I'm giving you some points in world coordinates. And I'm asking you to figure out what pixel in image space, where in image space, will this point land, right? Where will it go in image space? So that's what you're about to do. It's really not too bad, I promise. Before we do it though, I want to get just a smidge of intuition in your head. If you were a human, which I assume you all are, if you were a human and you were standing at the optical center of your camera and you were looking out into the world, where would this point be? Remember, these are millimeters, right? So where would this point be, right? Are we talking about miles away? Is it inches away? Like, is it, I guess those are imperial units. It's not that helpful, but, you know, could you walk to this point? Do you have to get in a car to drive to this point? Is the point right in front of your face? Where is this point in the world? How would you describe it in words? Remember, our units here are millimeters. How would you tell someone to get, how would you get from the optical center of the camera, where let's assume you're standing, to our world space point that we want to map, right? How would you get there? How far away is this point? Just what would you tell someone? Yeah, maybe 500 inches, okay. Let me add a little detail here. So if you're standing here, right, for example, let's talk about W for a second. So the W axis, that is the direction of that you're looking. It's kind of the direction straight ahead down the camera, like down the lens of the camera. So this point, I'm saying it's 10,000 millimeters straight. That's the W dimension, right? So to get to that point, one of the three things you have to do is go 10,000 millimeters straight ahead. How far is 10,000 millimeters, just roughly? So it's like how many meters? Yeah, 10 meters. Okay, cool. So yeah, so it's like 40 feet, 10 meters, like 11 yards, something like that. So yeah, it's like you could walk there pretty quickly. It's like the end of a hallway or something, right? So if you walk down a hallway 10 meters, right, we're kind of getting there, but you're not all the way there yet. So you walk down a hallway, for example. And then this U, this is telling you, okay, go 1 meter to the right. So go 10 meters straight ahead, go 1 meter to the right, right? And then what is this telling you, this negative 200? Which way is that telling you to go and how far to find this point? So not back, good guess. Which way is it telling you? Away, kind of. Yeah, so Hernan is close. It's not actually down though because it's negative. It's actually up. So look at V. V is positive down. Yeah, so it's up. So this is saying go 10 meters forward, go 1 meter to the right, and go 2 meters up. That's where the point is, right? That's where the point that we're going to map to image space is. And again, why is it up? It's up because notice our coordinate system is positive down. That's why the arrow points down. So a negative V value means go up. Okay. So we have some point in the world at those pixel values. If you're driving in a car, for example, this would be, you know, a few car lengths ahead. It would be a little to the right, but still in your lane, and it would be 2 meters above where you are. So maybe it's a bird or something, right? So this is some point in the world. And I'm going to give you 60 seconds now, maybe 90 seconds. And I would like you to figure out X and Y. So at what pixel location in the image will this point land? So I'm going to go ahead and go on mute for like I said, 60 or 90 seconds. And your job is to find X and Y. So I've given you everything I need. There's no trick here. So give it your best shot. You can all solve this problem. Take 60 seconds and we'll chat about it then. Okay, hopefully you've had a chance to think about it a little bit. Let's go ahead and hop into the answer. This one's not too bad, in my opinion. This could be a good quiz question. So here's my math on it. So really all we have to really do is plug into these equations. So we have our x equation here. So I'm going to plug in the u value. So the u value is 1,000. So the 1,000 goes there. And then phi x, that's 1,000. So 1,000 goes here. And then I'm dividing by w, which is 10,000. And then I'm adding 960, which is delta x. So if I do all that, I get 1,000,000 divided by 10,000, which I think is that 100? I think it's 100. 6 zeros over 4 zeros. Is it 100 or I think it's 100? Let me know if I'm wrong. I think the answer here is 1060. I believe we get 1060. And then here, this is the same equation in the y direction. So I've got negative 2,000 as my v value. I've got 1,000 as my delta y value. I've got 10,000 as my w value down here, and then I'm adding 540. So negative 2,000 times 1,000, I think is negative 2,000,000, I believe, divided by 10,000. You take off 4 of the zeros, and I think you get negative 200. So I think I get 340. I think I get 340. Hopefully that's close to what you either got or what you were starting to compute. Let me know if I made an error, but I believe that that's the answer. And that's the idea. So it's pretty straightforward. So if I have some pixel that's out there in world space at these coordinates, right? And I want to figure out where it belongs in the image, right? This is all I have to do. So all I have to do is plug it into the equation. It's going to be at pixel location 1060, 340. That is what these equations do. So not too bad. Hopefully that's not too scary. Let's keep moving. Let me know if there's any questions on that. If not, let's keep moving. And I want to get you to another question. So let me share my screen here. Cool. Okay. So here's my next question for you. And again, we'll pause for 60 seconds or so. So if you look at this question with me now, it's very similar. But now notice that I've given you x and y. And I would like you to find u, v, and w. So it's very similar to kind of what I'm doing here, right? So I have pixel locations and I'm trying to map them to world space, right? So what I'm asking you to do here is to take this x and y value, 200 and 100, and I want you to find u, v, and w. So I'll go ahead and go on mute again for about 60 seconds, and then we'll come back and talk about it. So good luck. Please try to find u, v, and w given x and y. Okay, so I'm going to go ahead and unmute here. Any ideas? So let's do this one a little differently. So I kind of showed you my solution first before I hop into mine. Any answers? So yeah, if you have an answer, go ahead and throw it in the chat window. What do you think? What is the location in world space from this point in image space? What do you think? Did anyone get an answer? Hopefully the last problem made sense. So Hernan says, is it possible? Okay, well, why might it not be possible, Hernan? What are you thinking? Yeah, so Ravina says 2 equations, 3 variables, right? So yeah, so you might have figured this out. I'm kind of trying to trick you a little bit, and not to be mean, just to kind of push your understanding a little bit. So the problem I've just asked you to solve has no answer. It has no answer. And if someone asks you why does it have no answer, right? You could give the linear algebra answer, which Pooja and Ravina have correctly. You said, hey, you've only given us 2 equations. But you've given us 3 unknowns, so we can't solve it, right? Which is true. But I would like you to give me a more intuitive answer, right? So your answer is right. It's correct in as far as linear algebra is concerned. But yeah, intuitively, why is it impossible, and Abhijit's starting to hit on it here, why is it impossible to, in the general case here, map from image to world coordinates, right? Why is that impossible in this case? Why is there no one answer? Can anyone expand on, Abhijit has a great start. Can anyone expand on that? Why is this impossible? Data's not there, sure, but I want to give me a more intuitive answer, right? Well, I mean, why is there not one answer? How would you explain this to your grandmother? Why is there no one answer? And let me ask you a little further, you know, there's no one answer, but is there a set of meaningful answers if there's no one answer? Is the answer just we don't know, or do we know something about it? So let's think together for a second, right? So what's the problem here? Let's look at the problem closely, right? So I have some point, some pixel, right, xy, and I want to know where did that ray of light come from, right? Where is this point in the world? That's what I really want to know. Now, if you think about it for a second, right? If you're just a little camera sitting here and there's some point in the world, let's say that this point, instead of being right here, what if this point was like right here? What if it was still on the same ray? This is a ray of light. What if the point was right here, right? It would look exactly the same as it does as if it was right here. So any point along this ray is a valid solution to this equation. And if you wrote out the equations, which I hope you did, you should actually end up with an equation that has 2 variables, and that's actually the equation of a line in 3-dimensional space. So any point along this line is a valid solution to this problem I've asked you. So it's not just that there's no answer, it's that there's an infinite number of answers, but all of those answers are along one ray. And intuitively, if you were explaining this to someone like your grandmother, I would say something like, hey, cameras cannot measure distance. Cameras cannot measure depth. They don't have depth perception, right? They only have a 2D projection, and we can only guess about how far away something is, right? But you do know, you don't know nothing, you do know that it's along this ray, which is important. That'll be important soon. I hope that makes sense. So I think hopefully I've set us up well for an important question then. So here we go. So I was, saying, hey, I made this animation back in my old job, blah, blah, blah. And I said, look, I have mapped from image space to world space, right? Here's image space. I took those pixels, I put them in world space, right? And if you look here, right, I claimed that, hey, this 3-dimensional map of a city of Amsterdam, this was made from a bunch of 2-dimensional images, right? So think to yourself for a second, right? I've shown you what some people can do using this kind of math, right? You've seen some cool demonstrations. But also, I've just shown you that doing this is actually kind of impossible, right? I've said, hey, we can't actually solve the equation. There are an infinite number of answers. They're all along the same ray, right? But we can't solve it, right? So let me ask you this then, right? And Abhijit's getting onto something for sure. There's kind of 2 levels to this, and we'll get into them. But when I made this animation at work, I did something, there's different ways to solve the problem. Let me ask the class this first. If you had to solve the equation for this case, and you wanted to make a really simplifying assumption that would allow you to find the coordinates in world space, what would you do? Any ideas about how you could change the equation? And let's just take this case. So forget about this for a second, right? There's a simplifying assumption we can make in this case, which is exactly what I did and what I'll show you in the code soon. What assumption could we make in this case that would make the problem solvable? So Abhijit says fix the depth. That's a great guess. That is incorrect, but a very good guess. Sean says, is any ray cross-section a particular position value within a given frame? Yeah, so I think, Sean, you're kind of getting at the idea of taking multiple views of the same thing and taking intersections. We'll get to that soon for sure. I did something much simpler here. Monica says a constant distance. So no, I didn't assume a constant distance. What else could I do? What assumption could you make in this problem that would allow you to solve the equation? There's one other thing that no one has mentioned yet. And look at where these points are getting projected, right? You can kind of see this little cone getting projected out. So close again, Abhijit saying depth is the y-coordinate. So to make this plot, to do this, I made an assumption that's actually kind of common in driving applications. I assumed that the world was flat. I assumed that the world was flat and that the car was fixed relative to that world. I might have actually included some up and down, I can't remember, but if the world is flat, right, you can actually constrain one of your 3 dimensions. Let me show you real quick. So if we go back to this problem that I asked you about, here we are. If the world is flat and your camera is at a fixed height relative to the world, which of these 3 variables is actually fixed? One of these variables will not change. Which of these 3 is fixed? If the world is totally flat and we're just looking out over the world. Yeah, it's V, right? So V, the vertical direction, that would always be like 2 meters if your camera was 2 meters over the ground. So to make this animation, and I'll show you the code in a minute that does it, I assumed that the camera was X distance over the ground. That's it. That allows you to solve that equation. There's more complicated ways to solve the equation, which we'll get into soon, but I think we only have a couple minutes left. Let's see, where do I want to leave you for today? Maybe I should have left you with that question. That would have been better. So we're going to get into the intrinsic matrix, then we're going to talk about homogeneous coordinates, and then, like at the end, like I promised, we're going to talk through just briefly how to actually, so if you're interested, all the code you need to do this is at the bottom. I take an image, I do the math to project that image into world space, just like I kind of promised at the beginning. Here's kind of the ending result. So I think we'll pick up here next week, on Thursday, excuse me, and we'll kind of just finish this out. I want to get to this overall equation. We've talked about the intrinsic matrix so far. We haven't talked about what's called the extrinsic matrix, which you also need. So we'll get into that, and then we'll start next time. We will get into depth in, let's see, what is lecture 2 here? Lecture 2 is interest point. Yeah, that's going to be a big lecture. Yep, this could be weeks easily. So we're going to talk about interest point detection next time. So I hope you enjoyed today's lecture. The 3D stuff is really, really cool, I think. So we'll finish up this lecture next time. Make sure you hit up your reading. Your reading is in a book called, it's from this author, I can't pronounce his last name, but it's a really good book. He's going to talk about how to detect interest points. And we're going to talk about how do you find points to do that triangulation to build 3D models. So that's what we'll talk about next time. And yeah, hope you guys have a good week. We will talk to you on Thursday. So Adam says, kind of funny, and you can stop the recording anytime, Rohan, thank you. Kind of funny that 600 years ago during the Renaissance, the Y were going in the opposite direction with linear. That is super interesting. Yeah, so I think what Adam's talking about, during the Renaissance period, right, there's a lot of advancement in how people did paintings, and they did the same exact, it's called projective geometry. Some mathematicians were figuring out the math at the same time. And if you just change a couple variables, it's basically what we're doing today. Like, it's super similar. That's super cool. Okay, guys, well, have a great week. We will talk to you on Thursday.